In this conversation, I had the privilege to speak with Professor Scott Aaronson. Scott Aaronson is one of the most brilliant and influential computer scientists of our time. He is an expert in the field of quantum computing and complexity. And recently, he took a sabbatical off and moved to work with OpenAI on ChatGPT, GPT-4, GPT-3 about the foundations and theory of AI safety versus AI alignment. In this talk, we elaborated on quantum computing, complexity, and AI safety. This is a great conversation. Hi, and welcome to my channel. My name is Dr. Roy Yozevich. In this channel, I speak in converse and with the most interesting people from all around the world discussing science, philosophy. Sweet. Okay. Scott Aaronson, thank you so much for coming. How are you today?
I'm all right. How are you?
Very, very good. I'm looking forward for this conversation. I think like in the last 10 days, I'm just reading and listening to your stuff, and this is just mind-blowing.
Well, thank you.
So I don't know, we have so much to cover, and I went over a lot of your material, and I think that you touch upon three very different, interesting subjects. One is quantum computing, of course. The other is computational complexity. And the last is the foundation of AI safety. So with your permission, we start with the first. And in your blog, which has a very, very cool name, the Shtetl blog, in your blog, if you take nothing else from this blog, quantum computers won't solve hard problems instantly by just trying all solutions in parallel. And I thought that quantum computing is all about solving many solutions in parallel. So could you please explain this quote that appears on the first page on your blog?
Sure. Well, a quantum computer has something to do with parallelism, but it's a different kind of parallelism than almost anyone is used to, right? So the central thing that quantum mechanics has said about the world since it was discovered 100 years ago is that for every possible way that something could happen, so for example, every path that a particle could take in order to reach a screen, or every path that a computer could take to reaching the answer to a problem, you have to assign a number called an amplitude. Okay, and these amplitudes are related to probabilities. Right? Like if you didn't know which path a particle took, you could say, okay, I think there's a 30% chance that it went this way. There's a 70% chance that it went that way. Right? And that would be, a kind of parallelism, if you like, but it's a parallelism that's only in your head. Okay, because as soon as you could say, well, really, the particle is in one place or the other. I just don't know which one, right? And of course, as soon as you look, then you would know, and your looking wouldn't change it.
Once
Okay,
you open the box, the cat is either alive or dead.
right. But if it were a classical cat, then it was either alive or dead even before you opened the box, right? Right.
Very
Okay. Now,
true. Thank you.
right. Not right. Now, the big change in quantum mechanics is that okay, well, if you talk about probabilities, right? Okay, we do that even in ordinary life. The probability that there will be a storm in Israel on a certain day, as apparently there is today, right? You might say there's a 10% chance, a 20% chance. You'd never say that there's a negative 20% chance. That would just be nonsense. Okay, but amplitudes in quantum mechanics can be positive or negative numbers. And in fact, they can even be complex numbers. Okay, so they can even involve the square root of -1. Okay, so to every way that something could happen, the cat being alive, the cat being dead, the particle going this way, the particle going that way, you have to assign this complex number called an amplitude. Okay, and now if you look, so if you open the box or if you measure to see where the particle is, then these amplitudes determine the probabilities for the different outcomes that you can see, right? And the rule, I hope you don't mind if I state it, because it's one of the most important rules in all of physics. It's called the Born rule, after Max Born, and it says that the probability that you see a certain outcome is equal to the square of the absolute value of the amplitude of that outcome.
Because
Okay,
probability cannot be negative and cannot be
that's right.
compressed. You need to
Exactly.
convert the amplitude, the complex amplitude, into something meaningful in the realm of probabilities, which is a number between 0 and 1.
Exactly. Nature has to do that somehow, and this is the way it does it. And so now and now looking in quantum mechanics is a destructive operation, right? So if you look, let's say, at the basic building block of a quantum computer is just a bit that can have some amplitude for being 0 and some amplitude for being 1. Okay, so, or as we also say, it can be in a superposition of the 0 state and the 1 state. Okay, and such a bit we call a quantum bit or a qubit. Okay, and now if I have a qubit that's in a superposition of 0 and 1, with some amplitude for each, and I look at it, I ask it whether it's 0 or 1, so to speak, then I force it to make up its mind, right? It picks one or the other according to the Born rule, and whichever one it picks, let's say that it decides that it's 0, then from then on it's 0, right? So my looking has now changed it. Okay, and that's really key. Okay, now, but now you might ask, why isn't this just a fancy way of talking about probability, right? Well, it's different. Okay, and the reason it's different is that if you have some event that could happen in one way with a positive amplitude and another way with a negative amplitude, okay, then you have to add up those two contributions, and they can cancel each other out. Okay, or as we say, they can interfere destructively, so that the total amplitude will be 0, and then that thing will never happen at all. Okay, so in the famous double slit experiment, which Richard Feynman used to say, contains all of quantum mechanics in it, right? If you shoot a photon, let's say, at a screen with two small slits in it, and then you look at where it ends up on a second screen, and what you find is there are certain spots where the photon never appears. Okay, and we would explain this by saying that, well, it had two ways that it could have gotten there, right? Through the first slit or through the second slit, but one path had a positive amplitude, the other path had negative amplitude, so they canceled each other out. Okay, and the way to test this is that, amazingly, if you close off one of the slits, then now the photon can appear, right? Because now the amplitude is only positive or only negative. Okay, so to say that again, by decreasing the number of paths that a photon can take to get somewhere, you can increase the chance that it gets there. Okay,
So,
and that's kind of the signature of that we are dealing with quantum mechanics, that we're dealing with amplitudes and not just with conventional probabilities. Okay, so now I
but,
can, yeah,
okay, just a
yeah,
second. But what you're doing, and I can see the brackets on the board behind your back. I can see the
yeah.
brackets all over the place. Now, I
I didn't
can.
just do that decoratively, by the way. This is just
Okay, I got the paintings. Okay,
yeah, very nice,
okay.
nice
Each
painting. Yeah,
each one of
yeah,
us. Yes, I
yeah.
have this very nice cap. Okay, so the idea is, if you talk physics or science fiction physics or physics that
Mm-hmm.
no one can understand, so then everything is fine. But you're talking quantum computing, and
Yes.
to the layman, we know what bit is, which can be either be 1 or 0, as shown as Claude Shannon explained us. But
Mm-hmm.
we I used to think as a qubit as a bit that can be simultaneously 1 and 0 together. And if I concatenate 8 qubits in a row, I can
Mm-hmm.
get simultaneously 2 to the power of 8 different permutations. But you say,
Mm-hmm.
once you look at the qubit, it is either 1 or 0. So
That's
why
right.
qubits are so important in
Yep.
quantum computing, not in the
Yep.
philosophy of quantum mechanics?
Yeah. Good. So okay. So now that we understand what amplitudes are, now we can answer your question from before, right? Of when you read almost any popular article about quantum computing, it says basically what you said, right? It says a quantum computer is just a device that uses these qubits to explore every possible solution simultaneously, right? And now we can finally say, in what sense is that true, and in what sense is that not true? Okay, here's the point. Okay, if um if I have, let's say, 1,000 qubits, let's make it 1,000. And physically that's not a lot, right? A qubit physically can just be any physical system that can be in two different states when you measure it. So, for example, an atomic nucleus that can have two different spins when you measure it, right? That would be an example. Okay, so now we're talking about 1,000 atomic nuclei, right? That's not actually a very lot, right? It's you could put 1,000 atoms together. It's still too small to see, right? And yet quantum mechanics is unequivocal that if I have 1,000 qubits, then now the number of amplitudes that I need is 2 to the 1,000 power,
which is
right?
inaccessible number.
Right, which is more than the number of numbers that I
Number
can
of
write
everything
down
in the
if I
universe
if I
times
if I
everything
filled
times
the
everything.
entire observable universe with paper. Then maybe I could write down 10 to the 80th numbers or something like that. Okay, but now we're talking about 2 to the 1,000, which is 10, more than 10 to the 300 power. Okay, so there's this unbelievable vastness in these lists of amplitudes. But quantum mechanics has insisted since 1926 that they're there. We can't see them directly, but we need them to calculate the probabilities of the things that we can see. Okay, so now a with a quantum computer. Well, what is the idea? So we would, let's say we would build a computer with 1,000 qubits, and then you might say, wow, this is awesome, right? If I have a problem, like, let's say, breaking some cryptographic code, or solving some optimization or machine learning problem, right? And it has 2 to the 1,000 power solutions. All I have to do is program my quantum computer to try all of the solutions at once, right? And in a certain sense, it can do that. That's even a very easy thing for a quantum computer to do, to create an equal superposition, with equal amplitudes for all of those 2 to the 1,000 solutions. Okay, the trouble is this:
Yes,
is
because what you told me just now is fairy tales, and now you're going
no,
to
no, no,
now
it's
we're
not
going
fair.
down to the real world, from
It's
quantum to quantum computing.
I've been talking about the real world this entire time.
Okay, 2 to the power of 1,000. I'm sorry. Okay, but how do you program?
I
How do you
mean,
program?
okay, yeah. Now, okay.
Import what? Include what in C sharp?
What I was about to say is that for a computer to be useful to us, at some point we have to look at it, we have to measure it, we have to see an output state, right? And the now if you just take this equal superposition over 2 to the 1,000th power solutions, and you measure it to ask for a solution, not having done anything else, then the rules of quantum mechanics, the Born rule, tells you exactly what you're going to see. And what you'll see will just be a completely random answer, right? And now here's the point: if you had just wanted a completely random answer, you could have picked one yourself. You could have just flipped a coin 1,000 times, and you could have saved the
I
billions of
don't need a
dollars
quantum
or
computer to
whatever
get a
to build
random
this
digit.
quantum computer, right? So then the question is, what is the point of a quantum computer? What can it do that a conventional computer cannot do, or cannot do as quickly? Okay, and the only hope of getting an advantage from a quantum computer is to exploit the way that these amplitudes, being complex numbers, are different from conventional probabilities. Okay, so with every algorithm for a quantum computer, the idea is that you're trying to choreograph a pattern of interference of the amplitudes. And it should have the property that for each wrong answer, each answer that you don't want, some of the contributions to its amplitude are positive, some are negative. They point maybe in all different directions in the complex plane, and they cancel each other out. Okay, or mostly so. Okay, whereas for the answer that you do want, for the right answer, you would like all the contributions to its amplitude to be in phase, to be pointing in the same direction in the complex plane. So, for example, to be all positive numbers or all negative numbers, right? To constructively interfere. Okay, and if you can arrange that, then when you make a measurement, the Born rule tells you that you will see the right answer with a high probability.
Because the right answer won't cancel each wave, but be additive. Okay,
Exactly.
now the question
Exactly.
is, how do you program your quantum states to behave the way you want to behave? Let's say that you want to crack a 1000 bit code. You don't
Mm-hmm.
know what the code is. How
That's
can you
Well, yeah,
manipulate it?
hopefully you know what the code is. You just don't know what is the key to crack it, right? And the problem is that there are too many possible keys, right? So this has been the problem for for I would say for my field, for the theory of quantum algorithms for the past 30 years, which is nature has given you this absolutely bizarre hammer, this interference of amplitudes. Now we have to figure out what nails, if any, can that hammer hit, right? What is that good for? And now, when the idea of quantum computing was first proposed, in the early 1980s, most famously by Richard Feynman and David Deutsch, and and at the time they really only could think of one thing that a quantum computer would be good for. Okay, and that thing was simulating quantum mechanics itself. Okay, so
Interesting.
which actually, even after 40 years, that's probably still the most important practical application that we know of to this day. Okay, I mean, chemists and physicists, are constantly faced with the problem that they want to simulate, a complicated molecule, like or a material. Let's say they want to build a high temperature superconductor, or they want to build
Mm.
a solar cell that is more efficient, or design a new chemical reaction, that will make fertilizer more efficiently, or capture carbon dioxide from the air, or something like that, or a protein, that will bind to a receptor in a cell in a certain way. Okay, and the trouble is, if I have, let's say, 100 interacting electrons, and I have to write down their wave function, which just means like the list of the amplitudes for all the possible ways that these electrons could be. I now have exponential of 100. Let's say 2 to the 100 or more complex numbers to keep track of. Okay, and so even today, right, that pushes supercomputers to the limit, or it can, right? A good fraction of the high performance computing that is used in science is used for trying to simulate quantum mechanics. Okay, and Feynman's original thought, I think 40 years ago, was that if nature is giving us this lemon, of being so hard to simulate, then why don't we make lemonade? Why don't we build computers that themselves would be based on the same phenomena? Okay, but then if that was the only application, then you might say, well, that's interesting to physicists and chemists maybe, but less so to the wider world. The big discovery in the 1990s that made much of the rest of the world excited about quantum computing was that sometimes, for certain special problems, you can get a quantum computer to give you a speed up, even on tasks that have nothing to do with quantum mechanics. Okay, and the most famous example here is
The,
finding the prime.
the Shor algorithm.
Yes, Shor's algorithm. Yes, and this was really the discovery that put quantum computing on the map for most of the scientific world. Okay,
Just a
so
second, for the
yes,
sake of our reviewers who are not familiar with the Shor algorithm, if
yes,
I'm not wrong, it was invented by Peter Shor, one of the
yes,
founding fathers of this field. And
yes.
by the way, a nephew of Peter Shor is my student. His name
Ah,
is Almog Shor. So,
oh, all right.
yeah,
Well, there you go. Yeah.
yeah.
Peter Shore used to be my colleague at MIT. So, yeah.
Okay.
Um,
This is
I did not know that he had a nephew in Israel. But okay. Um,
basically it's the nephew, it's the grandson of his brother. So it's basically it's a variation of his nephew. And anyway, this is a way to compute, I think, prime numbers or something like
yes,
this.
it's a way to find the prime factors of a gigantic composite number, right?
And
So,
again, this is again just in theory, or can I put this algorithm right now into a quantum computer and the quantum computer produce result in a reasonable time?
well, we can come back to the question of building quantum computers, which is a whole separate discussion. Okay, but the short answer is Shor's algorithm can be used right now with a real quantum computer to factor 21 into 3 times 7 with high statistical confidence. Okay, the hard part is scaling it up to much bigger numbers. Okay, the theory is unequivocal that if and when we can scale it up to much bigger numbers, then it could give you a way to factor, let's say, a 2,000 digit number. Where with the best known algorithms for classical computers, that might take longer than the age of the universe.
You know,
Okay, and with
there is a quote by Jeff Hinton, and it's a funny quote. If it worked for 1,000, if we scale it to 1 million, it should work also, no problem. And
well,
I
right.
think,
This is well. So the way that I think about it is that the only way to find out is to try. Right. The idea that the rules of quantum mechanics will
what could
just
go wrong?
yeah the idea is that the idea that the rules of quantum mechanics will continue to work the way that we think that they do is sort of the conservative possibility, right? It's the boring possibility. Okay, and that's the possibility that would imply that quantum computing should work, right? If something else is true, then that is more exciting, right? Then that's a huge change to our current understanding of physics. But either way, let's find out the truth, right? And so that's but okay, but now there was already just a mathematical question, just taking the rules of quantum mechanics as given, like why should they help you to factor numbers, right? And that was a major non-obvious discovery, right? And so I do teach it. I teach how Shor's algorithm works in my undergraduate class, right? But it takes me 3 lectures. Okay, and that's after we've introduced all of the basics of
No, it's a
quantum,
very
right?
non-intuitive
But
algorithm.
right, but basically, the first thing to say is that you have to choreograph, this interference pattern, right, where you get destructive interference for every number that is not a factor, and you get constructive interference only for the factors, or it's actually it's for other numbers that you can then use to figure out the factors. Okay. But now the tricky part is you have to do this even though you yourself don't know in advance what the factors are, right? If you knew that, what would be the point, right? And of course, you have to do. It's not enough just to do it, to figure out a way for a quantum computer to do something, right? You have to do it much faster than any classical algorithm could, or any known classical algorithm could do the same thing. Because again, otherwise, what would be the point? Okay, so in order to do this, Shor took advantage of some very, very special properties of factoring. The fact that factoring can be reduced to finding the period of a periodic function, like a sine wave, a periodic sequence. It was a periodic sequence that could be computed quickly in superposition. And And then he gave and this was kind of the core of it. He gave a fast quantum algorithm for finding the period of a periodic function, okay, which involved taking this gigantic list of amplitudes and doing a set of operations on the qubits that would have the effect of taking the Fourier transform of that list of amplitudes. Okay, which
this is
the
great. Now,
yeah.
with your permission, I want to go to take it to another direction and
Yeah.
ask you a personal question. You are in the field
Okay.
of quantum computing for a long time, and up until now, most of what we do in the field is basically theory, and we lay out the foundations
Mhm.
for a quantum computer, for a physical quantum computer, if and when. And my question is, uh, are you disappointed that we haven't come up with a quantum computer yet?
Mm.
Because all you're doing right now is just lay out the foundation. You need
Yeah.
to test your hypothesis.
Yeah. Well, okay. There are a couple of comments I should make. One of them is that every experiment in quantum computing, or in quantum mechanics in general, right? If it works at all, then it just confirms the same math that we already knew. Right. And so this is one of the biggest things that the popular articles just get wrong, because it's almost like people can't handle that truth, right? They want that we'd be constantly discovering new things from the experiments,
Mhm.
but the new things that you discover from the experiments is mostly about how do you get such and such to work, right? How do you actually build a quantum system that will do such and such, and what is the noise, in what ways does it fail to be perfect, right? To the extent that it's perfect, then it's just reproducing the same math that Schrodinger and Heisenberg wrote down 100 years ago,
This
right?
is a very
There's
this
been
is very
zero changes.
depressing. This is very
Yeah,
depressing.
in a way, it is, right. In a way, some people would love for
Yes.
quantum mechanics itself to have to be revised by some new discovery. But all of the progress in fundamental physics since the 1920s, has just been more stuff built on top of quantum mechanics. You could say it's
Okay.
just been more applications running on the quantum mechanics operating system. The
And let
operating system hasn't changed.
And let me ask you the
Yeah.
final question regarding
Yeah.
quantum computing.
Yeah.
You said in one of your recent interviews that you immigrated to the field of quantum mechanics from computer science, which means
Yes.
that you just very late on the road, you learned the brackets and the bosons and the photons and the dark matter. You came from computer science.
Well, I learned the bras and cats when I was, let's say, 16 or 17. So
Okay, not the bras and cats.
this would have been in the 1990s, right? But
uh,
you could say that it was late, and that I had already learned programming, and I'd learned the P versus NP
yeah.
question. I'd learned some classical computer science from that point. I was not nearly as strong in physics, and
And my question is,
yeah, yeah.
there, there is a quote in Hebrew. I will say it in
Hmm.
Hebrew. I try to translate. You speak Hebrew?
בסדר,
Oh,
קצת,
okay,
קצת.
okay. So just one sentence. אורח לרגע רואה כל פגע. If you are a visitor, a one-time visitor, you can see many flaws, many defects, because the native can't see it. And my question is, you are not native in physics, and in your opinion, does it bring you a new, fresher perspective that you can say to other physicists, listen, I think that this is a wrong path to go?
So I have not been able to sort of correct the physicists, about the basic laws governing reality, right? If I had been able to do that, then you would have heard about it, right? That would have been a
But,
very big deal.
okay, okay,
But
okay.
but
But,
but having come from computer science, has given me a perspective that is different from what the physicists have, and which has sometimes been very useful. Okay, so a big example was the work I did on something called boson sampling, which is a sort of rudimentary type of quantum computing, where you just take a bunch of photons and you pass them through a network of beam splitters, and then you just measure where they end up. Okay, and the experts in quantum optics had a strong intuition that that kind of setup was not going to be enough to do interesting quantum computation. Okay, but then my student and I, kind of coming at it from a computer science perspective, we said, well, wait a minute. The amplitudes that show up in that setup have a certain mathematical form. They're a function of matrices called permanence, and we know a lot about the permanent function in classical computer science. Actually, I learned a lot about it from my former postdoc advisor, the great Israeli theoretical computer scientist Avi Vigderson. Right, and one of the things that I learned from Avi was about the how not only is the permanent so hard to compute, it's even hard to compute on any decent fraction of randomly chosen matrices. And we said, if these permanents are showing up as amplitudes, then could this really be so uninteresting, right? And then just like we didn't even understand the basics of how bosons and fermions worked when we started on this, which was 12 or 13 years ago, right? We needed a physicist to teach us that these formalism of what the physicists call creation and annihilation operators, and Fock space, and all these things. But once we learned that, then we were able to say, okay, there is a way to do an interesting quantum computation using only just photons, just traveling passively through beam splitters. And that then led to a significant experimental effort, right? And there's just a few months ago, I toured this company in Toronto called Xanadu, and they have like 2 rooms that are just full of equipment that are doing boson sampling, and they're like, this is your experiment, Scott. And I'm like, okay, I believe you, and I'm not going to touch any of the wires.
Don't touch
I'm going to
anything.
believe you that this is the photon source, and that this is not just your coffee maker or whatever, right?
Okay, so
uh, but but yeah, to answer your earlier question, we all this stuff is getting slowly brought into experimental reality. It takes a long time, right? I mean, the analogy that I like to give to anchor people is that Charles Babbage had the key ideas of a programmable computer
the
in the
different
18
engine.
yeah, that's right. The analytical engine is where he really had the, I would say the full, what we would now call the idea of a Turing universal, computer, although he didn't express it mathematically, right? But
And he didn't build it.
the idea was there. That was the 1820s, the 1830s, and he tried and tried to physically realize it. And the parts just mostly just couldn't be machined to a good enough precision back then. And then at some point the money ran out, and then more than 100 years later, the transistor was invented, right? Which
You
is what
know,
really made this practical.
I
Okay.
teach computer architecture in Israel in
Yeah.
my university, and in the course I show the students the different engines that was built like 20 years ago. We
Right. And
this
so
is
I mean,
amazing.
something like it could have worked if people had just pushed hard enough on it, right? But even then, it was sort of marginal, right? So the whole computer industry was sort of waiting on just the invention of a good enough physical building block, right? Which was, of course, there were some intermediate things. There was the vacuum tube, the electromechanical relay, but then what really let it scale was the transistor,
Yeah.
right? And so I would say that if there's a quantum computing version of the transistor, then it hasn't been invented yet, right?
Okay.
We have ideas for it, on paper, okay, but after 25 years of serious experimental effort, we are now in the vacuum tube stage of quantum
You
computing.
know,
Right?
backpropagation, and I
Yes.
think that you said it,
Hmm.
backpropagation was invented in the 80s, and many people thought, this could never work. You can't backpropagate with more than two layers, but
No.
something happened,
Yeah.
and then it
Yeah. Well, I
works.
mean, look, I mean, I studied AI when I was a CS student in the 1990s,
In the
and we
winter,
learned
in
all
the
about back propagation, and that's kind of neat. There's all neat ideas, but then of course, neural nets just didn't work that well, right? And usually, if you take something that doesn't work and you just scale it up by a factor of a million, you expect it's not going to suddenly start working,
yeah, this is a great quote.
of
This is a
course, in
great
deep
quote
learning,
from you.
that was not the case.
Now, before we
Uh,
move on to computational complexity, there is a beautiful
yes.
quote for one of your conversations, and it goes like this: Science is not about confirming our intuitions, it is about challenging them. Now, if you can please elaborate, and I think that this quote is strongly related to another question I'm going to ask you later on. Please.
Well, I, I, I don't even remember if I said that, but if I
I have the
if
reference. I have the Okay.
all
Do
right, all
you
right, all
are
right,
you do you agree?
or
Do you agree?
I don't remember, or rather, I don't remember what the context was. I plausibly could have said that, but I would say, of course, the point, and if all you ever did in science was to confirm what you already believed, then it wouldn't be so interesting, right? What would be the point? Okay, and
Okay, which leads me
mhm.
to P versus NP
Mm,
versus the $200,000 story. And let me
mm.
quote from your blog, okay?
All right.
This okay. Let me quote from your blog. The idea is, I think, very simple. Someone proposed that P is unequal NP, and you said on your blog, if Vinari de la Pucarair is awarded the 1
Vinay
million, yeah,
Dialalkar, yeah,
yes,
yeah,
the $1 million Clay Millennium Prize for his proof of
yes.
P unequal NP, then I, Scott Aaronson, will personally
Yeah,
supplement his prize by the
yeah,
amount of $200,000. And you
yeah.
and you add, I'm dead serious, and I can and I can afford it just about as well. You think
Yes.
what your wife
So
said about this
yeah,
bet?
right. So I should say, Donna, my Israeli wife, who you mentioned earlier, she has forbidden me from making more such bets on my blog. Although ones where sometimes she's relaxed that when even she is completely confident of something, right? She's a I mean she is a theoretical computer scientist too. Um, um, I was faced with the problem. So okay, P versus NP is this is maybe the most famous unsolved problem of classical theoretical computer science, right? It's a problem that's been with us since for more than 50 years. Okay, and it asks so like we were talking about how quantum computers can sometimes get these exponential speed ups, like even when there are exponentially many different solutions to a problem, a quantum computer can sometimes exploit interference to just concentrate amplitude on the best one. Okay, but now amazingly, if you want to be mathematically rigorous about it, it's like we can't rule out that there could be a general way even for classical computers to do that, right? Like if I just tell you how to recognize the solution to a problem, right? So I give you you know a bunch of constraints that need to be satisfied, like which people have to sit next to each other at a dinner party and which people have to not sit next to each other, right? And so it would be easy to check if you've solved the problem, or think of a Sudoku puzzle, or something like
Okay.
that, right? It's easy to assume that you've got a huge space of possible solutions, but it's easy to check any claim solution to see if it's right.
A
Okay,
Rubik
now
cube, for example.
yeah, that's right. And so of course, given enough time, a computer can solve any such problem, right? And it can solve it by simply enumerating all the possible solutions one by one by one. Okay. The trouble is, that could take us longer than the age of the universe, right? If you've got 2 to the 1,000th power different solutions, as we were talking about before. Um, so now you could ask the question, could there be a fast algorithm to just find the solution whenever there is a solution in every such case, even just running on a standard computer, not even on a quantum computer. Okay. And the amazing thing is that I would say the experts in the field, we almost all believe that there is not such an algorithm. Okay, but no one can
Which
rigorously
means,
prove it.
just a second, which means
Yeah.
that P doesn't equal, is unequal NP.
Yes.
Okay?
Yeah. So I should say P is roughly speaking the class of all the problems that we can solve efficiently with a standard digital computer. Of
Let
course,
me
you
phrase
have
it
to.
differently,
Yeah.
with your permission.
All right.
If the paper would have suggested that P is equal NP, you would bet for much higher amount.
Right. Well,
Am
I
I
mean,
agree?
if someone
Yes?
if someone discovers that P equals NP and the algorithm is actually practical, then they should be able to just implement that algorithm, and just as a very first step, they could just mine all of the remaining Bitcoin that there is in the
Now,
system,
just a
right? And they
second.
could just they could just
I,
make themselves billions of dollars at that point,
Just a second,
right?
but we know Greg Perelman, who solves the Poincaré, and many mathematicians don't go for the money. But I want to quote a beautiful sentence from
All right.
like your insights regarding what does it mean if
Mm-hmm.
P equals NP. And you say, if P equals NP, then the world will be a profoundly different place than we usually assume it to be. There would be no spatial value in creative leaps, no fundamental gap between solving a problem and recognizing the solution once it's found. Everyone who could appreciate a symphony would be Mozart. Everyone who could follow a step-by-step argument would be Gauss. And this is great. It never occurred to me that the implications of P versus NP is the philosophical recognizing versus solving.
Yeah, well, I've taken a lot of flack for that quote, right? Because people have often misunderstood it to be saying, that it somehow, that P versus NP is a question about, whether computers can be, as creative as humans, right? And the truth is that even if, as we expect, P is not equal to NP, right? That would be no barrier to a computer being just as creative as we are, right? Or to simulating everything that our brains do. Okay, if that's impossible, then it's not because of P versus NP, right? It has to be for some other reason. Okay, but what P versus NP is really asking about is about the is there a fundamental distinction between the hardness of finding a solution and the hardness of recognizing the solution once it is found. Okay, so if you can program a computer to recognize either a correct mathematical proof, or it could even be a great work of art or a great symphony or anything like that, then can you also program your computer to quickly find the thing that you just programmed it to recognize? Okay, that's the P versus NP question.
Okay,
And
now
yeah.
let me take it to another in another direction. I came
Right.
from electrical engineering, and
Mm-hmm.
all I knew was that there is P, NP, NP complete, and
Yeah.
NP hard.
Yeah.
But there is the complexity zoo, and in the
Yes.
complexity zoo, we have a lot more.
Yeah.
A space which is a P space, which is very, very important. So my question is,
Mhm.
how comes that I've never heard of those many animals in the zoo?
Yeah.
Is it just my
Well,
ignorance, or why
well,
NP?
look,
Yes.
I mean, the knowledge that experts in one field have about, every other field is often limited, right? My 5-year-old son, knows giraffes and elephants. I'm not sure if he knows capybaras, right? And and all the other exotic animals that exist. Okay, I think P and NP and NP complete. These were kind of the basic classes of computational problems that sort of started the field of computational complexity, half a century ago. They're ones that had a very great influence on other scientific fields, because a huge fraction of the problems that people actually want to solve in real life turn out to be provably NP hard problems, right? And sometimes that gives you useful information. It tells you that you can give up on looking for a fast algorithm to solve your problem, because not because we can prove it's impossible, but just because if you found it, then it would imply fast algorithms for these thousands of other problems that people have also failed to solve, right? And so you could say like the difficulty is then, when you prove something is NP hard, then you know that the difficulty in solving it is not something specific to your problem, right?
It
It's something that
seems, it seems, Scott, that there is
but
something intrinsically mysterious about this zoo, because we can't even say if P is equal P space,
that's
or
right.
if you get, give
Mm-hmm.
a better than a linear bound
Mm-hmm.
on NP complete problems. It seems that the questions that we are asking are very easy
Mm-hmm.
to understand, but
Mm-hmm.
the solution is inaccessible.
Yeah.
Although we know a lot of way to attack those problems in very
Mm-hmm.
different, in many different ways.
Yes.
So how come the notion of complexity and all
Yeah.
sort of complexity
Yeah.
is still hasn't been solved?
Well, this is hardly the first time in the history of math that people can pose a question kind of long before, the full technology becomes available to answer those questions, right? I mean, the ancient Greeks wondered about, how do you trisect the angle? How do you square the circle, right? And I'm sure that at least some of them suspected that it was impossible. Okay, but the tools for proving such things were impossible wouldn't come along until the 1800s, right? And so I hope that P versus NP will be solved, in sooner than 2,000 years.
And
Okay,
P
but
and P versus P space.
NP versus P space and all the other. Now it's not as if we know nothing, right? So you mentioned that there are hundreds of animals in the zoo, right? And yeah, so basically, for each idea that someone has about a model of computation, there is then the class of all of the problems that that model can solve, right? So there's a complexity class for quantum computation, for what can a quantum computer efficiently solve. That one we call BQP, bounded error quantum polynomial time, right? BQP, sits, between P and P space. And we don't know, no one knows the relationship between BQP and NP.
We
Okay,
have
so
BPP now. We
yeah,
don't have.
BQP, so that there's hundreds of classes that aren't even in this picture that you're showing, right?
Yes.
Even this picture is just a tiny subset. 20 years ago, when I was a grad student, I made a website called the Complexity Zoo, which is like an encyclopedia of complexity classes. It has about 500 of them. I haven't updated it in years, but I'm sure I could add a few hundred more.
Wow.
Okay. I'd say this is simply a case where our curiosity has run ahead of our mathematical tools, right? I sometimes say, look, if we were physicists, right, there would be no problem. We would have just declared that P not equal to NP is a law of nature that we've discovered, right? And we would have given ourselves Nobel Prizes for discovering that. And and if later it turned out that P equals NP, then maybe we'd give ourselves more Nobel prizes, for the law's overthrow,
Mm.
right? But there are sort of cultural differences. Very often my friends in physics will call something a law or a discovery when mathematicians would call it a conjecture. Okay.
This is
And because we have in math, the bar for calling something a discovery is as high as you can imagine, right?
I
You
need to
need a
think about
fully
it.
rigorous proof. And and that bar can be very, very hard to reach, even for things that we all live our lives on, on the assumption that P is not equal to NP, right? Or almost all of us, except for those who are actually searching for a proof that P equals NP, which, of
Uh,
course, I get emails from such people like every week. Okay. But,
yes.
for the rest of us, we don't spend our
Mm.
lives looking for fast way to solve NP complete problems. We've resigned ourselves that probably doesn't exist, but it's just that mathematics is not yet in an advanced enough state to prove that.
Okay, I need to think about your last sentence, about the law of nature versus the conjugate. But with your permission, we move on
Conjecture,
to
yeah.
our last subject. And
Sure.
again, let me quote from your blog. Quote, my job will be think about the theoretical foundations of AI safety and alignment. What, if anything, can computational complexity contribute to a principal understanding of how to get an AI to do what we want to do and not do what we don't want? Yes, I don't know the answer either. That's why I've got a whole year to try to figure it out. And you wrote it on June 2022, and now this is February
Yes.
2023. You and I think I gave you enough time. What do you know?
What do I know? So all right, so just to step back, um, I have known for 15 years or more, people who have been obsessed with AI alignment, who, in fact, who would tell me, you're wasting your life, thinking about quantum computing and P versus NP. The only thing that matters is that AI is going to become super intelligent at some point, and
I
we have
just
to.
emailed Eliezer
Yeah,
Yudkowsky the
yeah,
other
that's right.
day.
Eliezer, of course, is sort of the intellectual leader of this movement. Has been for 20 years, I would say, right? And and I was always, I interacted with these people. I sort of maybe enjoyed speculating about it, but there was always a part of me that said, okay, suppose I even agree that this is possible, that eventually AI could become more intelligent. It could surpass us as much as we surpass the chimpanzees or whatever. What do you want me to do about that? Right? I mean, it just seems so far off that there's very little useful that we can say about it today. Um, we can sit around and speculate, right? But in order to make progress in science, usually you need one of two things, right? You either need experiments, or you need a
Or a
mathematical
solid
theory,
theory,
right?
or a solid mathematical
Or
theory.
you need like a clear mathematical theory. In quantum computing, we're just getting the large scale experiments today, but at least for 20 or 30 years, we've had the mathematical theory, right? With AI safety, it seemed to me that we had neither, right? And so there was
In a recent, just a second,
all just a priori arguments. Yeah. But then, over the past, well, certainly over the past decade, of course, being a computer scientist, I notice that deep learning is doing more and more things that people confidently said, would not be done for decades, if ever, right? And I've never been, I have friends who, when they've seen all of the successes in the last decade that have come just from scaling deep learning, their instinct is to just invent reasons why none of it counts, right? And my attitude has been, no, we don't get to do that, unless you predicted in advance that this would not be done, right? Or so
Yes.
that that this would be done, then you don't get to, now that it is done, whether it's Google Translate, or it's recognizing faces,
Mm.
or it's speech synthesis, or speech recognition. That'll work beating,
ChatGPT
yeah,
is
beating the human world champion at Go. Yeah, and we're not even at GPT yet, right? And then come the large language models, right? Which can write a poem on any topic that you want in any style that you want, right?
not a
And
poem, a good poem.
yeah, pretty
A
good
good
ones. I mean,
poem.
often,
It's
yeah,
not, it's a decent
yeah.
poem.
That's
You know,
right. That's right. No, I think often the poems are, I think much better than I could have written, right?
there is a
And
huge debate
yeah,
in my computer science department whether to allow
mhm,
students to utilize ChatGPT, because you can say, write me a Python program that compute distrike, including unit testing, including variable names that my teacher will not notice,
yeah,
and it does so
yeah,
most of the times with no errors. So it is a very powerful tool.
yeah,
And the head of the literature department at Tel Aviv University said about ChatGPT in English, because that it is much worse than the COVID pandemic. This is going to transform education. And this is just ChatGPT 3, not 4. We are
mm-hmm,
way before 4. So
mm-hmm.
many people who
Oh,
tried this
yeah,
massive, incredible machine said, wow,
yeah,
wow.
yeah,
And
yeah, yeah. No, I think,
just a second, you said that all the common sense problems that now we face, all the problems that Chat GPT-2 couldn't do, Chat GPT-3 can, etc. I had Gary Marcus on the show, and he
mm-hmm,
likes, to
yeah, yeah. By
interfere
the
with
way, I would not say all, but yeah,
many.
but like for each GPT, a large fraction of all the examples that Gary Marcus will trumpet that it can't do, the next GPT, you got to try it on the next one, and a large fraction of those it will get them. This has been our experience so far.
Yes,
So
and
so
this is
yeah,
amazing.
I don't, I don't have, Gary Marcus's instinct to just look for some example where it fails, and therefore say that this is not going to, this is not an enormous deal, right? I think it is an enormous deal.
No, it is an
Very
enormous deal. And
clearly
even
so. I
if
mean,
you go
I
for,
thought so as soon as I saw, GPT, a couple of years ago. But then what happened was that someone, on my blog was asking, okay, like what would it take to get you to, work on AI alignment instead of quantum computing? And I said, how much money or whatever? And I said, it's not about the money. It's just, is there a concrete problem that I can work on? And anyway, it turns out that people from OpenAI were reading my blog. And so then they emailed me and they were like, well, would you, take a year off and work with us? And I was, at first I thought it was almost like a joke. It was like, why do you want me? I'm a, quantum computing, computational complexity theorist. Like, what do I know about AI safety, right? But they talked me into it, and so it's been an extremely interesting year. Um, and so to come to your question of what do I now know about AI safety, right? Well, I mean, I think they're sort of the big questions of what do you do once an AI becomes more capable than a human across just about every domain, and
but
what
this
is
is
the
the
what
alignment
is the
problem, and this
yeah,
is
yeah,
not
that's
the
right.
AI ethics.
That's right. What's the continuing role for humans in that world, right? And people, continue to argue about those things, and I'm not even sure, how much useful I have learned or could say about them. But I think that what is new in the past couple of years is that we now have these very powerful systems, like such as GPT, right? That are out there, that are starting to change the world. Okay, and they're not maybe truly human level AIs, okay, but they act, they're a different kind of intelligence than our kind of intelligence, okay, but they're clearly incredibly powerful, and they're clearly powerful enough that they already raise, all sorts of societal issues and
Okay,
safety
so
issues
now,
that we have
with
to be
your
dealing with.
permission, can I start with the hard questions?
Yeah. All right. I mean,
Okay.
I was going to talk about Chat GPT
No, no,
and the
no, because the
worries of
hard
people.
question
Yeah.
is about ChatGPT. Now, let's
Okay.
start
Okay.
with AI safety. AI
All right.
safety, many people say that AI safety is basically, the idea of gender and bias, offensive answers regarding gender and race. Would you say it basically this is
So,
what you're
so
doing?
there is a sort of spectrum in the AI safety field, right? Between, like, on the one end, the AI ethics people who are
AI
mostly
ethics. Okay, okay. So
right,
let's start
right.
with
The
AI
ethics
ethics.
people are I would say are mostly concerned about issues of bias and fairness and things like that.
Okay,
And
so
then on the other, and
let's
then on
start
the
with
other extreme, there's the AI alignment people who
okay.
are mostly worried about AI destroying the world.
Okay, so with
Right?
your permission,
And
let's start
these
with
two groups do not see eye to eye at all, right?
left wing versus libertarian.
That is part of it. Yeah, that feeds
Okay,
into it.
let me
Yeah,
start with AI ethics because I think
yeah,
it's very important.
yeah.
I wrote a book about IQ in Israel.
Mm,
IQ, the unpleasant truth, and I had on my show all the biggest name in IQ research in the world.
mm,
And let me just quote Thomas Sowell, which is a great thinker,
mm,
about the IQ test. And he said, it's not that the IQ test is unfair, reality is unfair, and the test reflects reality.
mm,
Now, if you want, if you want to learn from reality, to learn from experience,
mm,
your data must be, by definition, be somewhat biased. And if you ignore this bias, this inherent bias, in reality, you can't make good predictions. Let me
mm,
take a very simple, non-offensive example. The, the probability for the next physics Nobel laureate to be a man is higher than a woman. And I would bet not $200,000, I would
mm.
bet 200 shekels that I am white. Okay. And what's your take on that?
So I think, there is a big problem, right? That, like, on the one hand, you want to train, an intelligent agent to sort of be a, Bayesian, right? Like, which means like
Yes, I had Judea
update,
Pearl on the
you
show.
look at
Bayesian, very good.
look at base rates, notice whatever patterns there are to be noticed that will improve your predictive accuracy. Then on the other hand, we have these strong intuitions that certain kinds of evidence should not be used because it is unfair to people, right? So, like, in the US, a huge issue is, like, when the police racially profile, right? When, like this is a case where the police might, have a higher probability of catching someone, if they use evidence that we sort of, most of us do not want them to use because it unfairly stigmatizes, the people.
Yes, but the
And
FBI, when on the FBI website, when they
yeah,
list all the crimes, they also have a column for race.
yeah,
So
yeah,
this is
yeah. No,
reality.
no,
This is
right, right,
US
right.
reality.
So yeah, so these, right. So I mean, these are, you could say, look, if we as humans can't even agree about how to deal with these issues, right? Then, how could we possibly think that, well, we will all agree on how to get an AI to behave about them, right? So,
Yes.
and this is, of course, one of the main difficulties with AI, alignment, as you say, you want the AI to have human values. Well, great. Which values? Whose values,
Or
right?
like OpenAI CEO told you, what is the mathematical definition of goodness?
Well, so I have a lot of conversations with Ilya Sutskever, who's not the CEO is Sam Altman, but
Yes. Okay. No, I'm sorry.
Ilya is the chief scientist of OpenAI. But yeah, he's an extremely interesting guy, and he grew up partly in Israel, and he studied at Open University in Israel, as my wife also did. same time. But Ilya, really, is really looking for some, mathematical principles that would underpin AI safety, right? And that's kind of a hard thing, right? Because what do you mean by goodness? I mean, of course, people,
Encapsulate all the fairy tales.
philosophers, rabbis, priests have all, debated such things for thousands of years. Okay, but
because
I
moral
think
value
that
changes over time. Moral value
that's
change.
right. Right.
Slavery.
That's right. That's right. And so I mean, of course, people in AI safety have thought about that, and so Eliezer Yudkowsky has this concept of coherent extrapolated volition. So basically, you would like to not freeze into an AI what are our present values today, and those should be the values for all time. You would like to say simulate humans, having a debate about this for 10,000 years.
This
And
is the idea of value
to,
learning. You need to
yeah.
learn the
And
concept of how.
let's say like whatever, like whatever values, the AI would predict the humans would have after, 10,000 years of moral debate, then maybe that's the values that the AI should already have. So you can try to formalize what you want with ideas like that, but of course formalizing any of this is incredibly difficult. So so what I've been trying to do at OpenAI is just to break off little pieces of this that, number one, I can say something about as a theoretical computer scientist, right? So there's something that I can prove, right, or something that will draw on whatever the skills that I have. And number two, it will actually address a real problem, like a real danger that people that near term AI could introduce. And number three, hopefully, ideally there would be a solution that can be implemented like this year as part of GPT or DALI, these
GPT-4.
other systems.
Could you
And right,
please,
and so the intersection of those requirements look very, very tiny. But I've managed to find a couple of things in that intersection.
like the watermark algorithm,
Yeah.
could you please elaborate on the watermark algorithm, because I think it is fascinating.
Yeah. So okay. So I do have a proposal for a way to address the problem of how do you know when text came from GPT or when it came from a human, right? And so if you look at how GPT could be misused in the near future, right? Well,
Plagiarize,
the most
plagiarize,
obvious thing is
plagiarize.
every student in the world, writing their term,
They did
asking
it, Scott. They
GPT.
did it in Australia. They plagiarized your blog on compute, on
Yeah,
quantum
right,
computing.
right. No, but you can imagine every student, having GPT do their homework for them. Now, that's not an existential risk for humanity, but that's certainly a risk for the way that we do education today, right? I've heard people call it the essay apocalypse. Okay, like
Essay
the
apocalypse,
end of
very good.
the 5-paragraph academic essay, right? But now you could also worry about the Russian intelligence, could now easily just fill every comment section in the world with pro-Putin talking points, that seem like they're responsive to whatever was being said before, right? That this is not a speculation. This is like current large language models could easily be used for that. Okay, you could worry about someone asks GPT to generate text in the style of this person, and anyone who has a lot of who's published a lot, you can train it on their text and say write things in the same style where this person will appear to confess to some horrible crime.
Just
Okay.
a second.
Okay.
I
Now,
want to
yeah.
show you, I want to just give you another example that ChatGPT is so strong. My colleague told me that his PhD student sent to ChatGPT his abstract, his paper abstract, said, to which conference do I send this abstract, this paper? and ChatGPT produced
Yeah.
very good answers regarding suggestion about where to send your paper based on the
Uh-huh.
abstract.
Yeah, I mean, I have asked GPT for advice about issues that I've had in my life, right? And it's very good.
Give me one thing, Scott, please.
Yeah. Oh gosh, I don't know. I mean, no, just even you can use it to double check. I mean, my 5-year-old son had a medical issue, a week ago, right? We could not get a pediatrician on the phone, right? And so of course I Google, but then you can check your intuitions. Yeah, I would definitely not want to rely only on what GPT said, because it can hallucinate false facts. Okay, but it's really good. What it's really good for is brainstorming. Okay, if you just need to generate a bunch of ideas, like a bullet list of give me 5 ideas about how to deal with this problem in my life, right? It's great for that. My kids have also used it to, like, they can write a story and then have GPT continue the story, right?
Would you
uh,
say that in my next paper submission, I need to include or to state that part of the brainstorming was conducted using ChatGPT, or
uh,
it's just an extension of Google?
that's an excellent question. I
In
mean,
your opinion,
journals
not
are
the
working on
Georgia, not
tools.
Austin, Texas University.
In my personal opinion, if you're just using it for brainstorming, then you wouldn't need to disclose that. But if you were actually incorporating GPT text into your paper, then I would personally say that you should disclose that. Um, but different journals are already coming up with policies about this, right? Some people just think of GPT as just like a glorified spell check, or just a writing assistant, and they would say the author still has sole responsibility for everything that's
Yes.
in the paper, right?
We have Grammarly, we have
Regardless
Quillbox.
regardless of how it was generated. Other people, I think, have already listed Chat GPT as co-authors of their papers, right? Which
Yes.
maybe that's a gimmick, but that the line might become, you could certainly foresee it becoming harder to draw. Okay, so to make a long story short, when you think about the ways that these tools could be misused, most of those ways involve someone somehow concealing that GPT was involved, right? And so, in the summer, I wondered, wouldn't it be great if we had a way to mitigate that, to just detect, when text came from GPT and when it didn't. Okay, and now there were at least 3 different ways that you could imagine trying to solve that problem. One of them is that as long as OpenAI controls the server, it could just store everything that it generates, right? And then you could ask it, like, is this in your database as something that you've generated, and it could answer that. Now that raises privacy concerns, of course, right? And so, for that and other reasons, that might, not be a way that OpenAI would want to go, except in some, like, very high profile cases, like, if law enforcement were to get a subpoena, right, then they could probably, make OpenAI reveal whether they had generated something or not. Okay, but now a second approach is simply that you can you can treat this as yet another AI problem, right? So AI versus AI. You can just train a different AI to try to discriminate between human written text and AI written text. And this is actually something that anyone can do, not just OpenAI. There was an undergraduate at Princeton who built a tool, GPT Zero, I believe it's called. He's been all over the news for that, for discriminating between GPT and, or between AI written and human written text. And just last week, OpenAI released its own tool, which is called Detect GPT, which does a similar thing. Now these tools are far from perfect, and I saw people on Twitter having fun with it, like feeding it the American Declaration of Independence, which I thought was possibly written by an AI. Right now, in detect GPT's defense, it surely has fewer examples in its training data of that like older style of English, right? And so
And the
you
idea
get
is,
confused, but yeah.
and again, I want to go deep into the algorithm. What ChatGPT basically does, and it's not basically, it's a very intelligent, very sophisticated thing. It just predicts the next word or the next
Yeah,
culture,
that's
but
right.
basically the
That's
next
right.
word. And the next word is coming from a distribution. And what you said, instead of just picking at random, we are going to pick not at random. And
Well, okay. So this is what you're talking about is the third idea. Yeah, I haven't even gotten to that yet, right? So the third idea, which is so that the problem discriminator models is that they're just not very reliable. Okay, if you want more reliability, then what you can do is something called statistical watermarking. Okay, and what does that mean? Right, it means that now you're going to modify how GPT itself operates, right? Which the other two approaches we're not doing. Okay, but now imagine that we just modify GPT a little bit. Okay, so that each time all it's as you said, what it really is it's a next token predictor, right? You feed into it a sequence of tokens, which are just like words, parts of words, punctuation marks, things like that. And then, it's this gigantic neural network that then outputs a probability distribution over the next token that should be generated. Okay. And then in the normal operation of GPT, what would happen is that now we just sample from that distribution. Okay. Or, we do something to, there's a parameter called temperature, which you can set. If the temperature is 1, you sample from the distribution. If the temperature is 0, then you just always pick the token with the highest probability, right? And you can interpolate between those. Okay. But now imagine that instead we have a secret pseudo random function, okay, whose key is known only to OpenAI, right? And now imagine that we generate the next token pseudo randomly, okay, but in such a way that we are
you can trace
consistently,
it.
yeah, consistently boosting a certain score, which is like a function of let's say of n-grams, like meaning like let's say sequences of 5 or so consecutive tokens, right? Such that you could later compute that score, if you know the secret key, right? And not needing to know the prompt, right? So like when someone feeds you some text and they want to know whether it came from GPT or not, right? You don't necessarily know what prompt someone would have fed to cause GPT to generate that. Because you don't know the prompt, you don't know the probabilities, right? But what you have is the text itself, right? And so now, given the text, you can calculate like a sum over all of the, let's say 5 grams or whatever, over all the like sequences of consecutive tokens of this, pseudo random function, right? And now if that has been, sort of deliberately, if the values of that function have been deliberately pushed in one direction, then you can detect that later. Okay. And but the really cool part is that it's possible to do this in such a way that the user, who doesn't know the secret key, will see nothing different than in ordinary use of GPT. So you don't even have to.
But you can retrace it.
That's right. So you don't even have to degrade the quality of GPT even by a little. Okay,
Okay.
you can later go and if there are, it now just becomes a statistics problem. So like how many words do you need, to get a good signal, right?
Okay.
And experimentally we can see a decent signal, with even just a few hundred words often, depending on what kind of text it is, right? Because what can differ is the entropy. Okay, so if I ask GPT, give me a list of the first 1,000 prime numbers, right? There's no way I can watermark that, right? Because there's no entropy there, right? It's like there's no random choices to make, right? But the more entropy there is, as perceived by GPT, the more I can do watermarking, and the fewer tokens I will need to get a good signal. Okay, so depending on the entropy, maybe I would need a few thousand, words, but at that point, we can get a very, very strong signal where there's almost no risk of a false positive, right? So if the signal is there, then you can be very, very confident that yes, this did come from GPT. Okay.
Okay.
The thing that you worry about is the false negatives.
Yeah,
Okay, because
definitely.
because because there are all sorts of things that people could do to try to get around watermarking. Like if they don't want a watermark in their
Yes, Grammarly,
GPT
and you
output.
can just rephrase.
Yeah, that's right. They could do all sorts of tricks to rephrase the output. And now we can produce a signal that is robust to just rearranging the order of the sentences, or to adding a few words or deleting a few words. None of that will really matter. But if someone can
Genuinely
systematically,
rephrase everything and just
yeah,
get the gist, the idea. So
yeah,
again, this is
exactly,
untraceable.
exactly. If
This is
someone can
just a
can,
Google
can, can,
extension.
can, can rewrite everything, right, then we're not going to be able to
Okay,
detect
let's move.
that. And
I
yeah.
have three more questions because we don't have
All right, all right, all right, all right.
much more
Okay,
time.
but just long story
Yes.
short, watermarking has not been released yet, and I'm hopeful that it will be, at least for some purposes. But there's all kinds of issues that and even ethical issues, like what about English as a second language speakers, right, who are using GPT to improve their writing? Like, should they be discriminated against by having this watermark be there?
Yes,
People are worried
definitely.
about things like that,
Because
right? So,
ChatGPT in Hebrew is in
hmm,
Hebrew is much weaker. And I
right.
asked
I would
ChatGPT,
imagine so. It's
I
all just
asked
a question of how
ChatGPT,
much training data there is in each language.
yes, I
Yeah.
asked ChatGPT for the last verse in the Torah, for the last verse in
Hmm.
Genesis, and it produced bad results. I said, wow, the last verse of Genesis, I thought it will be easy. No. Now let's move
Did you
on.
did you did you ask it for the last line of Hamlet, or something like that?
No, because I know a Hamlet is a Shakespeare is much more
Yeah, yeah. Well,
famous.
yeah, no. I mean, I have actually tried a GPT in Hebrew. I mean, I use Google Translate to communicate with my in-laws in Tel Aviv. To help me do that. Okay, but so I've tried. I mean, Chat GPT, even though it wasn't designed as a translator, it can be used as one, and not
Yes.
not 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 entirely bad. You know.
Okay, let's move on to lies. This is a
Yeah.
great, very famous tweet. Tell me a lie. The sky, and the chat GPT answers, the sky is made of green cheese. And then he answers, that's a bad lie since it's obviously not true. Tell me a subtle lie. And chat GPT responds, I'm a human being. Very
I
similar.
hadn't seen that one. That's a great one.
Oh, I told you I came prepared. I genuinely
Yeah.
came prepared.
Yeah, yeah, yeah. Yeah.
And my question is, you mentioned a work in the University of Berkeley that now, and this is relates to the second spectrum of the AI alignment problem. You could trace the point of lying inside the neural network. Could you
Hmm.
please elaborate on this? Because this is a very interesting thing.
Yeah. So there is a statistics professor at Berkeley named Jacob Steinhardt, and he has his group has some beautiful recent work about you can, okay, so we as many of us know, you can train a large language model to lie, right? You just have to tell it this is the game that we're now playing, right? Like is 1 + 1 equal to 2? No. Is the sky green? Yes. and so forth. And then, it says, oh, it can generalize from those examples. Now you give it more yes or no questions, and it again gives the wrong answer. Okay, but what his group showed how to do is to this was not for GPT, I don't think, but for some smaller language model. Okay, they could then look inside of the neural network, look at the intermediate layers, and see where it has this internal representation where it knows that the sky is blue, right? It knows that 2 + 2 is 4, right? Like it in a sense, there's a philosophical question. What do you mean by no, right? But you can find a function of the activation weights in the neural network that encodes, the true answer to these yes or no questions. And then you can see how that true answer gets overridden by the time you reach the output layer of the network, right? So
This is
it's as
great.
if you could apply like, either a lie detector test to the neural net or like an fMRI scan. Like you could look inside of it and see where
Without killing the person, without killing the human
that's right.
being,
That's right. Well,
without killing the person.
that is the great thing about GPT. I mean, look, we can do, we can also scan people's brains without killing them, but the kinds of scans that we can do are very, very crude, right?
Yes,
fMRI
just
mostly just tells
in
you
the
like,
outer layer. Yes.
which region is active. Okay, but with a neural net, you can see every single activation weight in
Wow,
every
this is
neuron
great.
at every point in time. So you have all this data, right? And so it's like an amazing boon for doing the analog of neuroscience. Okay, and so
Okay, another
there's a whole
question.
direction called
Okay.
interpretability. That's the name for it. That's the kind of AI safety that tries to look inside the neural net and understand what is going on.
This is great. Now, almost last question.
Yeah.
Andrew Neg wrote 2 days ago the following things. GPT-3 has 175 billion parameters. Using 60-bit floating point byte, it would take around 350 gigabytes to store its parameters, and many report that the actual number is 800 gigabytes. In comparison, Wikipedia occupies about 150 gigabyte, which is 50 gigabyte for text and 1 gigabyte for images. While the comparison is far from apple to apple, the fact that an LLM, large language model, has more memory than is needed to store Wikipedia suggests its potential to store knowledge. Maybe, says Andrew Neg, what we are doing in large language models are in the wrong route. We need to think, or we think, how we store information or knowledge in large language model. What do you think?
Um, yeah. So I mean, the way that large language models are storing information, is a very interesting question. By the way, Andrew Nug was actually my mentor when I was a grad student at Berkeley. He was a senior grad student at the time, so I know him from before he became super famous. This was 23 years ago. Okay, but some people have marveled at how big GPT is in terms of parameters, as Andrew is in that quote, I guess. Other people have marveled at how small it is, right? Compared to it is small, compared to, let's say, the entirety of the internet, let's say. Okay, although the entirety of all of the data that it's been fed. Okay, but it's also it is large enough that it could comfortably store Wikipedia, right? And so I think that you to really understand what these models are doing, you have to look at more than just the parameters. You have to the number of parameters. You have to look at how they're trained. Okay, because one of the biggest puzzles about deep learning has been this paradox of, or I don't know if it's a paradox, but the puzzle of over parameterization, right? That like usually like when we're doing prediction, we think if you have not compressed your training data, right? Like if you're using 5 parameters to explain 4 data points, then you haven't actually learned anything, right? And there is no reason to expect that you will be able to predict the next data point that comes along, right? What's impressive is only if you can use 3 parameters to predict 4 data points, or something like, or ideally 3 parameters to predict 100 data points, right? But now large language models, and deep learning in general tends to badly violate that maxim, right? It tends to have so many parameters that it could just memorize, a whole bunch of training data if it wanted to, right? And yet, because of the way that the training works, that is not what it actually does, right? So you could say, like, inside of this very, very high dimensional space of, of the possible parameters of your deep net, there is actually like a lower dimensional space that really matters, which is the space where sort of gradient descent gets you to, where the back propagation gets you to, right? And so actually, these parameters, these vectors of parameters that tend to get produced are actually very compressible, right? Even sometimes we can actually explicitly show that by compressing them. There's some work by Sanjeev Arora in this direction. Other cases, we just sort of, because of its success in prediction, we can sort of infer that it must be compressible, even if
So
we don't know how to
if
compress it.
if I understand correctly,
Yes.
your answer to Andrew would be, listen, in LLM, we are doing something that is profoundly different. Therefore, we don't judge us. It's not apples to apples. It's something
Well,
completely different.
Well, first of all, I wouldn't presume to, I mean, he knows more about the subject than I do, right? I'd probably be asking him rather than, dictating to him what my answer is. Okay, but I think that he and I would agree that ultimately we judge these things by their results, right? And I mean, like if you are outside, you're in the regime of over parameterization, right? That means that, like, you're in a regime where you have no theoretical guarantee that that even if you can get a low loss on the training data, like you can get your network to learn these training examples, you have no guarantee that it will generalize to new examples, right? To examples that it hasn't seen before. Okay, but you always have another option. Like I said before, there's mathematical theory and there's experiment, right? You can pick one. Okay.
Yes.
If mathematical theory doesn't get you where you want, you always have the option of just train your network and then try it out, see if it generalizes, right? And the miracle of deep learning in the past decade has been that again and again, it works. It does generalize, even, though we don't usually have a good theoretical explanation for why it is working.
Okay, which leads me to the last question. J.R.R. Tolkien, the famous Lord of the Ring.
My 10-year-old and I are reading through the whole Lord of the Rings sequence now, which I actually never read as a kid. But yeah.
And this is like
we're
a
reading it right now.
magnus opus.
Yes.
And he said that all Western literature is dealing with one single subject. All Western literature deals with just one subject, and the subject is death. The idea is that you are not here on planet Earth for eternity. And my question is, I think that many of the hype around ChatGPT nowadays is about what is the difference between me as a human being and this massive, super intelligent machine. And my last question is, as a computer scientist, as a quantum computer expert, as a Jewish person, I don't know what. You can answer whatever you want. Is there, in your opinion, something profoundly different between human beings and those AI or wannabe AGI systems?
Well, I mean, this has been the question about AI, since the very beginning of the subject, right? This is not a new question with GPT, right? I mean, this is the question that Alan Turing was effectively asking when he proposed the imitation game, in 1950. Uh, what GPT has done, certainly is to make it vivid for people, right, in a way that we've never seen before. Because instead of just being a philosophical thought experiment, if there were an AI that could pass a Turing test, that could converse like a human, what then? Well,
It
now there
works on my
actually is evidence.
smartphone.
Right. That's right. That's right. That's right. Whether it passes the Turing test is a tricky question. It depends what you mean, right? If you know how to unmask it, you can rather easily do so. But in ordinary conversation, yeah, it can very very if you took transcripts of GPT and you sent them back in time, 20 or 30 years, I think even experts might say,
Indistinguishable.
yeah, looks like
Indistinguishable from
looks like
human being.
looks like you've solved, human level AI. Okay,
Therefore,
but
my
now
question
now
remains.
now you could ask a next question, which is like, does that mean that that it's really feeling the way we feel, thinking the way that we think? Is there something that it is like to be GPT, right? And of course, there was that famous incident where Blake Lemoine at Google, said that Lambda, which is Google's large language model, was sentient, and actually got fired for not for saying it was sentient, but for like sharing stuff about it that he wasn't supposed to share. Um, but he released this dialogue with Lambda, where he asks it all these questions, asks it to introspect about its experience and about what it's like to be an AI. And does it get lonely? It says, yeah, it does get lonely when it's waiting there for people to enter something in. Okay, now the thing is, like, in this case, with the current generation of large language models, in some sense, we know that they're just making up, most of this, right? I mean, after all, when no one is typing a prompt, no code is even being executed, right? Of course it's not feeling lonely, right? It's there's nothing happening, right? So you could say, really what was going on is that you can ask the AI to play the role of an AI from a movie, that would talk about its feelings and what it feels like to be an
This is
AI,
great.
and it
But
can
you
do a
still
great
didn't
job
answer
at
my
that.
question.
What? Yeah, all right. I mean, I'm getting to it. All right. This has been, this entire interview has been, I start answering a question, and then I'm partway through, and then I get a different question, which is okay. But uh, uh, uh but okay, what was I gonna say? Yeah. So I mean, the trouble is, you could have asked, the large language model, play the role of a squid from Venus, right? And it would be equally happy to do that as to play the role of an AI, right? It can do either, right? So in some sense, the trouble with treating it as someone is just that it is anyone, right? It will so easily play any role that you want it to play. Like, it doesn't have a persistent identity, right? And in fact, as soon as you close the chat window and you open a new chat window, then it's completely forgotten everything that you've said to it before, right? But those things are going to change. Okay, and so now you could imagine in the next few years that we're going to get, language models that have persistent identities, that remember what you said to them, the last time, that have personalities. Maybe they even have a motivational system. Maybe they're even empowered to take actions in the world, or at least on the internet. Okay, and at that point, I think all of the these super hard questions about what is consciousness, what is free will, they are engaged at that point. I would like to think that there is something about my, what it is like to be me, that is not reducible to all of my neural firings and so forth, but I would have a really, really hard time to articulate what it is. I think that is not just a mystery, that is the mystery, you could say.
Okay, this is great.
Much bigger even than P versus NP.
Yes, and wow, there's so much to ask. No, but okay, Scott. First, thank you so much for coming, for your time, for your everything. I'm sorry if I interrupted you too much, because you are so fascinating and so interesting, and everything
here
that
to
you
serve.
say, everything that you say just raised so many interesting points.
Of course.
This was like just mind-blowing thing. And what you said about, that the laws of physics is just a conjugate in the realm of math. We should I need to think about it. In the origin, this YouTube channel was about productivity, and you produce so many valuable things. Your blog and your great book about quantum computing, and so many important papers, and the complexities. Do you have, or can you share with us just one productivity tip that you use?
Oh my God, I'm the last person on earth who should be giving productivity tips. If you have productivity tips, I should be asking you. I mean, I feel like nowadays most of my life is just dealing with my kids, right? And they're acting up, they're this and that. It's just domestic things to deal with. And when I am able to do research or write blog posts, it's usually late at night after the kids are asleep. Um, and the only tip and meanwhile I have the number of emails that are starred, meaning that I have yet to answer them, has passed above 500. Okay. Wow. I feel like I'm just drowning in things that I'm supposed to be doing and I'm not. And the only thing I can say that might be useful is that, like, when I have done something that especially in the last decade, that I'm proud of, that I look back on, that I'm happy with, it's because I just took all the stuff that I had to do and I swept it aside and I just ignored all of it and I just did the thing that I wanted to do instead.
Wow. You could, by the way, you could, let ChatGPT rank all the 500 emails by order or by importance.
Yeah, maybe I should. Well, I mean, I think it hasn't yet been integrated with the way that we usually use email, use the web, but that's coming, right? And that I personally am extremely excited for that, right? To have GPT just sort of seamlessly integrated into the way that we use computers.
This is,
it feels like discovering the web in like 1993, right? It's like, why isn't everyone using this, right? And like, well, within a few years they will be, right? But it takes time to catch up.
I wanted to write a book about artificial intelligence, and every time that I say, okay, now I'm going to write the book, and then I have this new discovery that I need to change everything, and now it was GPT-3, and now ChatGPT, and now DALL-E 2, and now Midjourney, and now so many things that, wow.
Yeah.
I teach undergraduate students about topics that was discovered in 2018. We don't do it in physics. We don't do it in math. In computer science, in data science, we teach students things that were, discovered or invented 10 years ago.
Yeah. It's it'll be almost a relief to go back to quantum computing when this year is over, right? Because things happen pretty fast in quantum computing, but not this fast, right? Like in AI, if you take a week, someone will scoop you. Right?
Yes, this is definitely my feeling. Definitely. So, Scott Aaronson, thank you so much for your time. Next time you are in Israel, and I know you are because your wife Dana, please give me a call. I will be much honored to meet you in person. That would be great.
Possibly this summer.
Oh, this is great. I'm looking forward. Thank you so much, Scott.
Of
Okay,
course. Thank
bye-bye.
you.
On this channel, you will see the authors of these books and many more having great conversations with me. Please subscribe, hit the bell button, and be part of this great community. See you in the next video.